I do not agree to being filmed. I said I do not agree to being. Are we starting now?
Yeah, awesome. Hello, everybody. We'll give it about five more minutes.
Okay.
For anybody to come.
Are you guys also sitting on 100% for internals? Or is it just me? Hello, Isuka.
All right, guys, we might make a start because it's late. Yeah, feel free to, I guess, ask any questions, but probably need to mention only genuine questions, please. Just for the sake of getting this done.
Okay.
Yeah, as getting this done as quickly as possible. All right, cool. So, just I don't have like an introduction slide or anything, so hopefully you've read what's on the Discord and stuff like that. But my name is Isuka, as you can see on the slide there. So today I'll be doing the physics masterclass, obviously. So I received 100 in physics when I graduated in 2021. So hopefully I can give you guys a bit of an insight for an overall kind of thing. So it is going to be a pretty brief one. So it's going to be a lot of overview of like what is physics overall. Well, what is covered in the physics syllabus overall. So obviously there is a lot of detail that is going to be missed because it can't be covered in like an hour and a half. Um, but yeah, that's what we'll be covering today. Do have a program set. Okay, cool. So I'm hopefully by this point you guys would know about when the exam is. It's on 10th of November, so probably exactly a month from now. Roughly paper one, paper two, it's split up. 20 MCQs is always, obviously, but you do have roughly 7 to 8 SAQs in the first paper, roughly 8 to 9 SAQs in the second paper, and they roughly equate to about 50 marks each. So they overall end up being about 100, maybe 110, 90, just kind of like ranges from there. But yeah, in terms of obviously the questions, you do have, your complex unfamiliars, as you probably noticed, is, quite a bit around electromagnetism, because there is a lot of, like, I guess, a lot of things you can combine there. So forces, electromagnetism, all can be combined together to make complex unfamiliar, and that's how they kind of built up, right? You do have a lot of data-based questions, and I'll bring up a file to help with, creating an answer, or a perfect answer kind of thing for the database questions. And then you obviously have a lot of quantum theory and the fact that, like, that's where the other calculations would be as well. But obviously you get, all of the other ones, the special relativity and all the other ones. All right, cool. So briefly, what we've been doing today. So summary of Unit 3. Unfortunately, maybe no Cahoots today. Sorry about that. I know I love Cahoots personally, but unfortunately no Cahoots. And then, so maybe some theory, some practice questions, similar for Unit 4, theory, practice questions. We won't be touching too much on Unit 3, just because we did cover it in our previous masterclass. So if you have any questions, if you want to go into a little bit of depth there, you can watch the recorded one. I am kind of monitoring the thing, the chat here. It says he said the strategy for database questions or strategy for explanation-based questions. Good question. So when I say this like a strategy, I mean like this, I've kind of built an ideal answer for graph, like it's graph/database questions. So they give a data set or a graph, and then I've kind of built a ideal answer for that. The unfortunate thing for an explanation-based question is not really a ideal answer because it varies quite a bit. So they could say explain Faraday's law, for example, and that obviously will differ quite a bit to explaining how, say, Lenz's law or any other law works. So it's more of an ideal answer rather than a strategy. So cool. And then I'll just briefly be giving any physics specific tips that I had, some general tips, so like study advice and stuff like that. And then hopefully we get to some Q&A at the end. All right. Okay. So we have 2 topics in Unit 3, 3 topics in Unit 4. So we'll just briefly be going on each one. I do have my iPad open here. So whenever we get to the questions, I'm just going to share this screen, my iPad screen, and then we're going to go from there. Cool. Okay, so we obviously know what projectile motion is, right? Anything that's projected. So any object that has a trajectory, a parabolic trajectory is basically considered projectile motion. Main thing obviously to know about projectile motion, you have X and Y axis, so horizontal, vertical. That's just breaking it down into its components. Important to know with horizontal. So the reason why you have constant velocity afterwards is obviously because of Newton's laws, right? So after the initial force, if there's nothing stopping it, then obviously it has consistent velocity, so there's nothing to stop that. Whereas obviously for the vertical axis, the y-axis, you obviously have gravity to stop it. So that's the forces that you have acting there. But that's pretty straightforward, right? Okay, cool. So key principle, yeah, they're both independent, of course. So that's exactly why you would have the Pythagoras to essentially combine them, right? Okay, just another question that's about Unit 4 about like the marking guide. Would you have any strategies to know where possible mark allocations be for an explanation question? Like if they ask explain the properties of light and it's a 6-mark question, how would you know where marks are allocated? Yeah, no, that's a really good question. First of all, to know where the marks come from is purely based on just doing a ton of practice questions and then like looking at the marking guide, right? But probably the best way is to break down the question. So usually, for example, right, if the question is like, explain the twins paradox and the light and the barn paradox, right? And it's like 4 marks or whatever, then it's like 2 marks each, and then just 1 mark of explaining it, 1 mark of probably like explaining how it is explained by special relativity, right? So it's very kind of like you have to know the ones that from the practice papers to kind of get an idea of what you would cover the mark wise. So it's I know it's a vague answer, but you get a bit of an idea once you start doing a lot of practice questions and you know what marking guides and you've seen a lot of marking guides, you know what marks kind of get allocated. But it's generally you break up the question into like categories, and then like one's for explanation, one's for, I guess, a conclusion, one's for, an introductory statement for like each of them, for example. So if there's two main topics of it, then you'd have like an introductory. So what is it, right? So in the case that I was talking about the paradoxes, what is the paradox? And then like, explaining what the paradox actually is. And then the final one is how is it resolved by special relativity, for example. So yeah, hopefully that kind of gives a bit of an idea, but yeah. Cool, kind of saying, okay, yeah, so very important thing here about projectile motion, and it kind of annoys me sometimes, but oh, whoa, that was not supposed to happen. In the textbook, I believe mainly Oxford, but I don't know if any other one does. They talk about it in cases. So they say case one, where you project it off the ground or something like that, and then case two is projected off like, like above the ground to something above that. And then the other one is like from above ground down to the ground. Please don't remember them as cases. They're not cases, they're not separate things. They're all the same thing, right? They're just the ball is somewhere else, right? You don't consider that a different case. That's just you're applying it to a different like scenario, right? They're different scenarios, but they're not different cases. So please don't try and memorize the formulas that you need for each case. Just apply the same formulas logically to whatever question that they give. All right. Because if you memorize the cases and the formulas, that's what you're wasting time essentially for that. So do not memorize those cases as that. Okay, so this one's pretty straightforward. You should know this by now for the formula book. So these are obviously the vertical motion ones, so the ones where the y obviously with it. Oh, sorry, I didn't see that. Could you please share the structure used for writing answers? Yes, yeah, I will bring that up when I get to it in the projectile. Well, I'm not sure if it's a projectile motion later on, but I'll definitely get to it and share that with you guys. Yeah, and then yeah, tip obviously resolve initial velocity into components, so you can bring that in. And this tip is kind of what we use later on for a question as well. Linear motion formulas versus the ones above. Hopefully you guys know the difference, right? Linear motion, it's in its name. It's only for linear motion. So anything traveling in a straight line, that's when you use the normal, like not these ones, the other ones in your formula book, the ones just above. If something's just traveling in a straight line, you use those formulas. All right. If anything goes in a trajectory, like a projectile or something, that's when you start using these ones because now you're breaking them up into components, different components. All right. So that's something important to mention there. All right, okay, this is the question. All right, just take a look at it briefly. So a basketball player shoots a ball at an angle of 55 degrees into a hoop on a post 4.3 meters away. The ball is released from a height of 2.1 meters and goes through the hoop, which is 3.0 meters off the ground. Determine the initial speed of the ball for the foul shot to be successful. Okay, so for this question, obviously, let me just share my screen really quickly. But for this question, it's not like a easy one, but it's obviously not a too hard one as well. All right. Okay, I'm not sure what you guys can see now. Okay, cool. Yeah, okay. So can you see also the PowerPoint as well, or can you just see that? Okay, yeah, no, you can only see the whiteboard. All right, it's okay. Hopefully you guys remember the question. So yeah, the question was a basketball player shoots a ball at an angle of 55 degrees. So if this was the stick man, right, they shoot that at 55 degrees there into a hoop, right, which is essentially 4.3 meters away. And then they shoot it off 2.1 meters, and then the hoop itself is 3.0 meters. And that obviously goes into the hoop there, right? Oh, okay. Sorry, there's a long question there in the chat. I'll come back to that question really quickly after I answer this, if that's okay. All right. Yeah, so that's 3 meters. So how do we work this out? So probably one of the good things to do, obviously there's like, some questions you can straight away just see it and you're like, okay, that's pretty easy. Let's just work through it. But sometimes it's just good to write down like the stuff that we have, right? So we obviously have the angle here, which is 55 degrees. What else do we have? So we have the S of X, right? So we've got the horizontal displacement, which is 4.3 meters, right? And then we've got, so 2.1 meters is the height to the ball and 3.0 meters is up to the hoop. So which means what is S of Y? What is the vertical displacement, right? Which is what, where the distance the ball is traveling, that would be what? 0.9, right? And then, yeah, do we have anything else from here? I mean, basically not, right? So with this, right, how does the theta become important here? Well, obviously when we break it up into components, right? So u of x is u cos theta, right? And the u of y is u sine theta, right? So that's where the angles will become useful. Okay. So as you can see here, we technically only really have like four values basically, right? So it's not too useful. And basically you won't be able to work this question out unless you do some substitution or ratio. So whenever you can't figure out a question, for projectile motion specifically, that usually means you don't have enough, which means you need to use a ratio or you need to substitute a value from one formula to another. So you kind of remove that variable, if that makes sense. So in this case, what we have is s of x, and we can use u of x here. So what is that formula? We've got s of x, u of x, t, right? So we have s of x. We somewhat have u of x. We don't have the u, obviously, but we can rearrange it. So t u of x over s of x, right? What is u of x here? Oh, sorry. I just realized I wrote that the wrong way around. S of x over u of x. So what is s of x here? We know we just brought it up there, which is 4.3. And then u of x is u cos and then 55, right? So if we want, we can just quickly calculate cos 55, which is 0.57. Technically, you can, if you really wanted to combine the 4.3 and cos 55 to make it easier, but we'll just keep it for 0.57 u of x, just because the value of cos 55, you know, might be useful later on as well. Cool. Okay, so now we have t. So I mean, that doesn't really give us much, but the point is that we can substitute t into something else, right? So something that has t, and obviously the only other value we have is s of y. So what's that? The only function that really, or sorry, formula that really has that is sy equals uy plus half gt squared, right? So yeah, it's gt squared, right? Okay, cool. So we just substitute everything into this. So s of y is 0.9, u of y is u sine theta or sine 55 here, plus 4. Oh, okay, this is a good question. What do you guys think g would be in this case, right? So we have already defined g as, well, not g, we've defined s going up. Yeah, good, exactly, negative 9.8, right? Because essentially we've already defined it going up, and then, oh, sorry, did I? Oh yeah, true. You're right, you're right. Good job. There you go. Guys pointing it out. Really good job. Okay, yeah, good point. So yeah, negative, exactly. So that would be negative, right? So really important to make sure you guys define like your axis beforehand. So this will be negative 4.9 t squared. Just for the sake of time, probably I won't just yeah, you definitely do, because you would like you'll just get a different answer, because obviously if it's a negative versus a positive, you'll be adding it versus subtracting it, right? So you would definitely lose marks there. Wait, in general, can we use the range equation, or is it more of an answer check tool? Are we restricted to do that? Range, oh, well, you mean the s of x uxt, I'm assuming. Okay. Yeah. Okay. That's okay. In terms of how many marks, I would probably say 3 marks, just for like this 3 to 4 marks. So probably like this formula usage, the substitution, and the answer, right? I won't bother going through the rest of it, because it's just a simple substitution from the S of 0.9, you sine 55 degrees, and then just substituting 2 here. So 0.43 into that, and then 0.43 squared into that. Okay. So hopefully with your display calculator, or just even a normal calculator, you should be able to get an answer for that. Yeah. If anybody does have an answer, feel free to chuck it in the chat as well. Yeah, sorry if I'm missing a lot of questions in the chat, just like, yeah, re-put the question if I've missed it or anything. All right, cool. So that's that question. So next on inclined planes yeah, so this one is pretty straightforward. I think this one was like a lot of the stuff that you learned for doing inclined planes you've done in year 11 forces, because that's kind of just like, learning about each force and how to like resolve force body diagrams, right? Okay, so we know inclined plane, anything that's just on a tilted surface, pretty straightforward. The only thing that it really changes is the FG, right? Oh yeah, I think so. Somebody raising their hand. Oh yeah, do you have a question? Sorry. Nope. Okay, guess not. Okay. So yeah, the only thing that it really changes is the weight force, right? Because as soon as you bring it up, you change the force, like you essentially reduce the force that's acting on each one, right? So you have down the slope, so which is essentially parallel to the actual slope itself. And then you've got the normal force, which is going up, and you got the weight force, which is coming straight down. So yeah, we've talked about that. And then yeah, weight vector as I mentioned, that's the main thing that just changes, right? F parallel is mg sine theta, F perpendicular is mg cos theta. If you guys don't know how those come about, like the actual derivatives, make sure you go over that. I know it's not tested, but it is important to go over that. Yeah, just make sure you like just know how that is. All right. Oh wait, I just realized I'm not sharing, bro. Okay. All right. There you go. Okay, cool. So yeah, yeah, that's what I was just talking about right there. Oh, rip, chat opened up. Okay, yeah, just a refresher of all of the forces there of the inclined plane. Just make sure you guys know all of that. So the weight force is going up. That's F perpendicular, F parallel, and you can see if that's theta, how big on theta for each one. Frictional force, if there is that, right? But mostly they just say friction is negligible. And then you've got the normal force, pretty straightforward. Cool. What is all right, cool. And then now just talking about circular motion. So again, straightforward, just anything moving in a circle. Velocity changes direction. Yeah, okay. So important thing to know here, right? Oh, please go back to the question. Oh, yeah, sure. All right. Um, like working it out. For the projectile motion question. Oh, can we use Solvay on calc to find U, or do we need to put working? Definitely need to put working. I mean, I'm not going to say definitely, but just for the sake of it, they do give marks for working out. You don't know where it is. Generally, it's substitution. So like when you substitute values in, but for a question like this one, the one we just covered, you won't really know where. It's most likely going to be like, like using the SXUXT, and then like substituting that T into the SY formula, and then the SY formula, working that out, and then probably the answer at the end as well. So that's probably like the marks that you get there. So definitely need to show uh oh, right, sorry, you mean yeah, this one, right? Is that the one that you're talking about, this question? Yeah. Okay. Cool. Yeah. I'll cover that in just a sec right there. Okay. Cool. All right. Real quickly then. Yeah. I will be covering that, so don't worry. Okay. About circular motion, right? Important thing is there is acceleration. So obviously centripetal acceleration. Why is there acceleration? Because a vector quantity, what does it have? Direction and magnitude. It's not changing magnitude though. So the actual speed, which is the magnitude of it, doesn't change, but the direction changes constantly, right? Which is why it's considered accelerating then, right? So we know centripetal acceleration moves into the actual circle, right? Velocity is perpendicular, pointing out of the circle. Centrifugal force is fictitious. Why do we think that it's fictitious? The main reason is that because it's working in a non-inertial frame, right? Because centrifugal force is only felt by the reference frame of the ball, for example, or when you're going on a ride at like the dream world or whatever, right? And then it's like spinning you around, you feel that pulling upwards. You're in the inertial frame of, sorry, non-inertial frame of reference, which is why it's considered a fictitious force. It's not an actual force, right? I mean, it is technically a force, but it's a fictitious force, right? Um, quick question about cyclic motion. Normally, they always give the plan to be horizontal, but what do we do if it's vertical? I don't expect, but I know it exists. Yeah, no, that's a good question. You get a lot of vertical ones in like, holy, you get a lot of the vertical ones in like different states, which is why I would recommend doing different state questions. The basically the main difference is when you put it into a circle, you have gravity to think about now as well. So gravity is pulling on different parts of it, right? I guess it depends on different questions, but definitely, um, I'm not gonna say it's not gonna be tested on QCAA, but to be fair, like I wouldn't really put it past them. Yeah, that's the like they'll give you a lot of information in the question, but just keep in mind now you've got gravity moving at every single one, right? That's the main thing. So when you're going upwards, in circular motion vertically, if you're going upwards, obviously you're going against gravity, and then when you're coming downwards on this side, you're accounting for gravity, right? That's the main thing that you need to think about. Um, no, they wouldn't ask if that why centrifugal force is fictitious. No, I don't think that's a syllabus point either. It's just something that they mention in the like I guess something good to know. But yeah. Um. Uh, okay. Right. I think are you able to do the question to show how it works? Yeah. Yeah. Sure. 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 All right. So let's do this question. I'm going to share my screen again on my iPad real quick. All right. Is it sharing now? Okay. Cool. Okay. So hopefully you guys saw that that question really quickly. Actually, what I might do is copy that question really quickly in to the chat, so you guys will have that. All right, there you go. All right, so yeah, now you guys have access to the question as well, so you can like kind of follow on. Okay, when I say golden rule, what is the golden rule here? So always when you're working with force diagrams, uh, isolate the systems, right? There's multiple things happening there, right? You can see that there's a circular motion, like a ball going in circular motion connected to a pulley, connected to an inclined plane, all right? So break it up, right? Firstly, break it up. And the other thing is important is to identify that object A is stationary. It's at rest, which means, right? So if we just like, really crudely draw this right now, that's a pulley there and then connected to this. Okay. So what we know is basically because this is stationary, whatever this is tension force, right? Whatever tension force is acting there is equal to the tension force acting here, which is equal to the centripetal acceleration acting here. Okay, that's the most important thing to know, right? So what is the tension? What is basically the tension force there? That's the F parallel force that we've been talking about, right? F parallel of G, by the way, just to keep in mind, this is obviously the weight force we're talking about when we're talking about parallel, right? So the parallel force, right, is equal to the tension force that we just talked about, right? This is equal to that. And then what's the tension force equal to? Tension force is equal to centripetal force, right? That's the only way essentially the object stays stationary, okay, where these all are equal. Okay, so and obviously there's no like friction or anything here, right? So what do we do first? We calculate because now we obviously have the force here, which is seven, not force, the mass here, which is 7 kilograms. So we can first figure out the FG parallel, right? However, yeah, you want to write that. Okay, which is 7 times 9.8, and then the angle. What is the angle? Right, 30 degrees. Right. Yeah, exactly. Right. Pretty straightforward. Sine theta. All right. So that's basically the main uh I don't yeah, I don't think it should be 2.21. That's quite small. I'll just calculate it real quick. 34.3. Yeah, cool. All right. 34.3 newtons, right? So that's the force that that parallel force, okay? And what do we know? This parallel force is equal to the centripetal force, right? And how do you calculate centripetal force? F equals mv squared over r, and that's all in the formula sheet that we have, right? So we know that 34.3 is equal to mv squared over r, and you just basically input everything from here, right? And like if you want to figure out the v, essentially just v equals the root of 34.3 r over m, right? And then you just substitute all of that in. Okay. Does that kind of make sense to everybody? Yeah, oh yeah, sorry. Yeah, I should have probably mentioned that. There's two different masses. So obviously the centripetal one, in the formula, you're talking about the one actually in circular motion, right? You wouldn't enter the 7 because that's inclined plane. That's a completely different system, remember. Just think about each system separately, right? This is F equals mv squared over r, and this one is fg, right? So those are two separate. So just keep in mind that. Make sure you don't mix the masses up, okay? Is this type of question as complex as circular motion gets? Um, I would say it's on the harder side. I just because of a question that I just remember in like specialist maths. I think it was in my 2021. There's a pretty hard one. I think that can like had circular motion, but that was specialist maths. Like it could go harder, but it shouldn't. Like if you use this golden rule, if you just like isolate each system, definitely definitely you'll be able to figure it out. Okay, because if you isolate each system, then you should just uh yeah. So yeah, you'll be able to like figure it out because from this identifying stationary isolating systems, you should be able to work out. It's pretty straightforward. That's the main thing, and that's what you should have learned in grade 11 as well. Because everybody just tries to kind of like work out like everything together, work at one thing at a time, work with the inclined plane first, work with the centripetal acceleration next, centripetal circular motion, right? Um, which is the best paper to do. To be fair, could you break down? Okay, so just best paper, that's a bit, I guess, like pretty hard to say. I mean, obviously anything QCAA related is probably the best. In terms of interstate, if that's what you're talking about, waste is pretty close to us. But if you want to really push yourself, VC, obviously HSC, those two obviously really do push. That's where I did see a vertical circular motion when I practiced. So yeah, that's something if you want to do vertical, circular motion, or anything hard. Could you break down the first step again? Yeah, so do you mean this step real quickly? Is there forces equaling? Is that what you're talking about? Oh my God, there's so many messages. All right, I cannot see the chat now for some reason because it's crashing out. All right, I'm assuming it's this step. So, okay, because we know it's stationary, right? And we know the only thing that's essentially like movement is the circular motion because you have essentially the circular motion spinning and then that's pulling essentially the string up and that string pulls, sorry, on the pulley, which pulls the mass, sorry, right? So essentially this circular motion force has to be equal to the tension here, tension pulling here. And what is the tension there, right? Oh, okay, cool. Yeah, okay, cool. Now it loaded. So yes, okay. So yeah, because this tension has to be equal to this tension. So on both sides of the pulley, this tension has to be equal to this tension, right? And then because this tension, right, where does this tension come from? That tension comes from the ball moving in a circle, right? So that's centripetal acceleration they're moving in, and that force is essentially pulling that in. So these are all essentially connected. This is one string just pulled to two sides, right? One from the pulling from the circular motion, one pulling from the inclined plane. Right. So that's essentially how you do it, right? Okay. The answer, um, it might be, I think I might have the answers open somewhere. Oh, I mean, actually, I could just calculate it really quickly if you wanted to. What is it? Yeah. 26. Yeah. 1.72. So 1.7. Cool. All right. Does that sound good with everyone? Any more questions? Hopefully, we can keep going. All right. Let's move on. All right. Gravitational force and fields. Pretty straightforward, these stuff, right? A main thing to do is I'm just going to pull up the document, the data question document while I'm talking here. But just memorizing the third laws, sorry, not third laws, the Kepler's three laws are really important. They do test you on that. And knowing that the third law is a combination of the universal gravitation formula, so the one with GG, multiple things, that's very important, right? To know that's a combination of that and the circular motion formula, right? Graph, questions in physical idea. Yeah, okay. And then basically just memorizing those three laws, and I say memorize lightly, okay? So make sure you don't memorize everything. It's just because these are three laws that you just have to know. Just memorize those. We know the Newton's law of universal gravitation, gravitational field strength. Okay, and
You're
then
still showing your iPad.
oh yes, sorry, thank you. Good point. Thank you for that. All right. I think my whole laptop is like slowing down now. All right. Hopefully. Okay. Yeah. Thanks for whoever that was. Thank you. All right. Yeah. So yeah, this is what I was on the slide. So yeah, just knowing the three Kepler's law are very important. The reason why I bring this up, I usually wouldn't bring like gravitational law or gravitational force and fields and orbits because it's such a like a low, not when I say low yield, it's such an easy, right? It's such an easy kind of like topic. But the reason why I do bring it is because they do bring a lot of the data questions from the gravitational force stuff, right? Which is why I'm going to be sharing this document. I'm just gonna close the chat. If you guys have any questions, just unmute because I think it's like slowing down my laptop quite a bit. All right. Stop sharing that. Yeah, this window.
Of universal gravitation. Force is attractive.
All right, sorry guys, bear with me here. My laptop is super slow.
Annoying.
Are you able to kick out the people who are spamming? Because it's slowing down everyone's computer.
I'll try.
Thank
Like,
you
yeah,
for bringing
I
attention to this.
Ban them, chat. Ban them. Ban them. No.
I'm not sure if I can. I'll just try it out really quickly.
Ban them.
But
Ban
yeah,
them.
it's slowing down my laptop so much.
Guys, can we just ask them to nicely stop, please?
Can we ban them, please?
Yeah, maybe Discord might have been a good idea.
Ellen, chat for the spammers.
Ellen chat, Ellen chat, Ellen chat.
Ah, I love you, Isuka.
Thank you.
Guys, Isuka's taking time out of his day to give us this, and you're just ruining it.
I know.
How do you think he feels right now?
Connor, apologize right now. Connor, apologize.
Thank you guys. Thank you. All right. Maybe I don't think I can ban them for some reason. Because I can't even mute anybody, which is annoying. If it does like I guess slow anymore, we can. I mean, I know it's annoying, but we could just like change to Discord because I don't think there's any more questions I have to go through anyway. It's
Yeah,
mostly just
100%, 100%.
yeah. Okay, yeah. Do you guys see the document now? Is that what you guys see right now? Yeah.
No, we can't see any. We only see you, bro.
Oh, okay. That's fair. That's fair.
We saw it a moment ago, though.
Oh, okay. Do you guys see it now? I click share on that. Oh wait, no. Hold on, not yet. Okay, cool. Do you guys see that now? It says it's sharing on my screen now.
Oh, yeah, we can see it.
Yeah, all right, beautiful. All right. Okay. So this is the graph, like the ideal answer thing to the graph questions. And the reason why I bring this up is because graph questions are so common. So I forgot exactly the values. I've got it written down somewhere, but it's bound to come in like the exams, right? Where they essentially ask, okay, well, they give you a data, they give a graph, they give a data set table, and then they say like, okay, create a mathematical relationship, and then from the mathematical relationship, calculate a value, right? So essentially they create a linear equation or something like that, and then they want you to essentially relate that to a formula that's on the formula sheet, and then basically explain that, right? These are direct copies of the marking guide, points of the marking guide that I've essentially identified. So all the graph questions I've brought, and then essentially copied off the the side, the marking guide like pieces, the points to address essentially. So these are direct copies of it. So and essentially, this is an example question, and I've essentially drafted in an ideal answer for it, which essentially covers all of this, as well as covering exactly what they need. Now, it might be going a little bit overboard, but it's always, it's better safe than sorry all the time, right? So usually it's a question something like this, as I mentioned, identify mathematical relationship between F and I. So in this case, it's F and I right here, right? And then make sure to always say as seen from the graph. I know this seems kind of pointless, but I do remember from a data test in grade 11, I think. I know it's like, really really like far-fetched kind of thing. But from a data test, I did lose a mark in grade 11 for not saying as seen in the graph. So just mention that anyway. As seen from the graph, mention what the actual relationship is. It is a direct and linear. Is it a positive? Is it a negative? Is it an inverse? Blah, 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 right? So we see here there is a direct and linear relationship between F and I. So write the proportionality constant there and the relationship. So this means because it's linear, we know that it follows y equals mx plus c. I'm really hoping you guys know that from methods in grade 10 or something. From the graph, it can be seen that the y zero, so we can see obviously that y is up to 0, even if it's slightly like off, like I've seen the marking guide sometimes estimated as 0. Yeah, which means c equals 0. Let m be the gradient, and obviously I go through the whole rise over run, obviously dy dx kind of thing. So change in y over change in x, which is change in force over change in current, and you insert it roughly. Obviously go from origin. If it goes through the origin, please make that one of the points. It just makes your life easy for you. Enter that value. Therefore, the mathematical relationship shows the following equations: y equals this, and then what is y and x? You just sub in force and current, right? And then, as I mentioned, usually after a relationship, mathematical relationship question, you have to determine some sort of value in the formula, and it's just a pretty simple substitution formula there. And oh, I don't think I finished it here. I think the reason why I didn't finish it because I think I did something wrong and I kind of was like Siebes and then didn't finish it. So this was a while ago, by the way. So yeah, that's probably the reason why. But yeah, this is what I would call an ideal answer. And I do have another document which I won't open just because it's definitely going to crash my laptop. But there's another document where I've compiled all of the questions, I think from 2021 and 2020, and all of the papers that I could think of. And I just copied all the graph and data questions there. So I could just copy all the marking guide stuff. And that's where I essentially built this from. So I'll definitely 100% take a look at this, and I'll, put in the Discord probably afterwards. I'll definitely take a look at this, and even if I say if I forget or something like that, make your own if you don't have one or if you don't have access to it, make your own, and then definitely practice it every single practice paper that you use, and then you're just gonna be like it's just gonna be like a mind numbing thing after a while. It's gonna be
Sorry
super
for
easy. So
interrupting. Might I
yeah,
ask a question? Okay, so
yeah.
when you mention the mathematical relationship, right, do you also mention the equation or just like the linear or exponential relationship?
Do you mean like y equals mx plus c? Is that what you're talking about?
Yeah, basically the equation they have given in graph. Do you just mention that directly in mathematical relationship or not?
So okay, hold on. Let me just share that screen again really quickly. All right. Do you mean the equation that they give in the graph here?
Yeah. Basically, do you
Oh,
mention it in mathematical relationship?
no. So this generally they don't give this. Like this, I think this is just because like a question that I probably copied off like a third party exam or something. That's probably why this is like on there. But generally they don't give this equation. If they do, it's more of like you can just check if your gradient's correct. That's basically it. And you can see roughly this gradient is 6.25 times 10 to negative 3, and that's basically 6.17, right? So it's like you can check it if there is, but you don't bother mentioning it because they want you to derive. And you can see if that from the number of marks of the question as well. It might be 3 marks roughly. And yeah, they wouldn't just expect you to just copy that in there and then expect you to just leave that there basically. So you'd have to derive it yourself for sure.
Oh,
Does that
okay. I
answer
was
your
Do you
question?
have any?
Just like my teacher asked me to mention the equation, So now I'm just confused on whether to mention it or not.
Oh yeah. So when your teacher said was she referring to the equation on the graph, right? This equation that I'm like
Yeah, this
circling.
equation asked me to mention that.
Oh, okay. No. So if you take a look at the ones on the QCAA, like the actual external exam papers, the mock pass papers, they usually don't have this equation on there at all. Actually, you know what? I'll try and bring it up. I'll try and bring up the other Word document that I've like copied all the answers in.
Okay, thank you so much for your time.
That's so good. That's so good. Sorry, somebody else had a question as well.
Yeah. Do you have any advice for questions where we have to graph the line of best fit ourselves?
Like the trend line.
Yeah. Like it's not
Oh,
given.
Oh yeah. So okay, actually, I think this might answer both of your questions. So I just brought it up the document. Okay, yeah, this is definitely slowing it up, but that's okay. All right, hopefully that's sharing now. You guys can see that. So these are the actual questions I just copy pasted from the official marking guides off the paper. These are like literally the question. This is one of the questions here. You can see that this they don't have the line of best fit or the trend line equation that they've brought here at all, right? And you can see a lot of the answers are there we go. Another graph question, no line of best fit, no trend line equation on the graph. Here you can see that haven't copied any equation from there. They've derived it themselves, so that you can see the c equals 0, the m, they figure out the gradient, they figure out an answer there. And yeah, there's like I've copied like a ton of them. But point is, so generally you will be working out the trend line. That's like they would have drawn the trend line. They wouldn't give you an equation generally. So you would actually have to try and find the trend line equation. That's what they mean by the mathematical relationship when they're trying to figure that out. That's essentially what they're trying. Does that answer both of your questions? Just speak out if that
Yeah, so
doesn't.
we basically like just find the equation by ourselves, and that's our answer, right?
Yes, that's correct. Exactly. So
Thank you so
yeah,
much.
that's all good. Yeah. So identify mathematical relationship. That kind of comes in two. So actually identifying what type of relationship it is. So whether it's a direct linear, whether it's like inverse, negative kind of thing. And the other one is actually figuring out, right? So that's essentially what you do. And yeah, again, as you can see, they don't bring the equation in. They don't have a trend line equation in there. So there wouldn't be anything for you to copy. I'm not saying that your teacher is wrong. Maybe just check what she's trying to say or what he or she is trying to say. Because like I could just be misinterpreting that, or like we could just be misinterpreting that. So just check on what she's trying to say there. But otherwise, yeah, that's what it is. All right. Cool. Let's head back to the PowerPoint. So that was the data questions. Oh, sorry. Does someone else have a question?
Yeah. When we find the mathematical relationship, does it? I heard my teacher said it's wrong if we put it in y and x form. It has to be in the whatever the y-axis is and whatever the x-axis. Is that true?
Yeah, that's exactly correct. Yeah. So yeah, I probably won't share it again, but if you saw in the ideal answer that I brought, actually, you know what? I might as well. So it's good for everyone, I guess. So I'll just quickly share this again. All right. Yeah, hopefully you guys can see that. So you can see at the end here, it's a bit like with all the equation editors that's going, it's a bit annoying, but you can see I put it into y and x form, then I converted it to the F and I, so the force and the current. That is very important. It's a really good question, by the way. So it's really important to convert it back to the y axis and what the x axis is defined by, because they want you to find the mathematical relationship between F and I, not y and x. So yeah, very good question. Hopefully that answered that. All right. Back to the slide. All right, cool. Okay, I think that's hopefully that's showing. Yeah, again, shout out if it's not. Cool. So moving on from there. All right, electromagnetism. So as I mentioned, I'm gonna fly through this part. First of all, because of time's sake, but also I covered this briefly in the previous masterclass. Whoops. All right. So what's high yield? I'm just gonna briefly talk about this. Electric fields. So particles in electric fields. So what happens to particles when they go into electric fields? What happens to particles when they go into magnetic fields? And what happens when pilot fields? I might come to this question at the end. This actually was posted by someone into the QSH, actually, and I thought it was a good question. I think it's from Interstate. I forgot who it was. I probably should have sourced that. But if somebody knows, please feel free to shout them out. This is a really good question. Yeah, I'll probably come back to it at the end because there is some more important stuff I'd say to go through. Okay. What's high yield, more high yield stuff? So let's go through quickly the review of what the phenomenon. Okay, what are phenomena, what we actually see. Okay, what's natural in the world that we actually see that's happening. Okay. When electrons go through something that's conductive, so a piece of metal, what happens? Electricity, boom, right? When there is electricity, what happens? A magnetic field, okay? And that's defined by Am's law, right? The right-hand Am's law. Okay, so that's what happens. Electrons in conductor forms electricity, a current, and a current produces a magnetic field. Okay, so now what if you move just a normal conductor through a magnetic field? So if you get a stick, right, like a metal stick, you have two magnets, you move it through it, what happens? It induces a current. You get electricity. All right, this is the science behind a generator. Okay, so whether it's a turbine, whether it's hydropower, whether it's even like, just normal fossil fuels, they create a steam, it turns a turbine. What does a turbine do? Turbine turns a coil, so you can actually see it there, right? There's like a person. This one is actually a person like moving it. But if you imagine if it's a turbine instead, it moves the coil inside the magnetic field. What happens? Current is generated. So that's how any generator works. Basically, any power generation apart from solar power basically is generated. It's using this concept basically, right? That's a generator, right? Generator is Fleming's right-hand rule. Just keep in mind, the image there, you have a hand. What hand would you use it? Well, I'm sorry for the left-handers, but generally use a right hand to crank it, right? So that means right-hand rule. Generators are right-hand rule. Motors are left-hand rule. So what are motors? When you move electrons through a conductor, which goes through a magnetic field. So you're putting a current through already, and it goes through a magnetic field. What happens to that conductor? It starts moving, right? That is essentially how motors work, right? So anything that, like a toy car, right? Like the RC car, whatever, right? They have motors, right? Teslas, right? It's essentially converting from battery to like motor, like to movement, to kinetic energy, right? That's, you get movement from that, right? So those are the main phenomena you didn't know, and that's motor, so it's left-hand rule, right? Motors are left hand, generators are right hand. No textbook has properly mentioned this, as far as I know. So I don't think you need to know motors probably don't need to know motors, but just keep that in mind. Okay, right hand is generators, left hand is motors, right? Solenoids, they're important. Oh yeah, someone's raising their hand.
My teachers have always taught that only use your right hand, and they've never taught us to use like our left hand for motors or stuff. So could you explain what you mean by like the left hand?
Yeah, that's a good question. Okay, so yeah, this is what I was kind of saying. They no textbook has explained it. Basically, they don't talk about motors because I don't think you get tested on motors, right? But I think it's really important to know, right? But essentially, when you talk about generators, so if there is essentially like the phenomena that I'm talking about, if there's a movement of a conductor through a magnetic field, how you determine the direction of current flow is using your right hand rule, right? So FBI, same thing, right? So force, magnetic field, current, right? Just make sure you identify in the question that is a generator. Most likely it will be because, again, they don't really teach motors, but that will be a right-hand rule, okay? And keep in mind, it's a right-hand rule like this. It's not the slap rule. The slap rule is the opposite. So if that makes sense. So if the slap rule is your left hand, this is a massive confusion, okay? So it's not slap rule is different, okay? It's the Fleming's right-hand rule. And I don't know why people learned the slap rule because like originally the Fleming's right hand rule is like with your 3 fingers like this. Okay. That is for generators. So if it's a motor where there's a current going through and you want to figure out the direction of the force, right? Then use the left hand rule. Okay. Actually, you know what? I think you should still learn it anyway. A lot of the interstate papers that you do will definitely cover like motors as well. I don't know why QCAA doesn't cover motors, but yeah. Does that clear that up, hopefully?
Yeah, could you just like I know how the directions work for the right hand rule. Like
Yeah.
for motors, since I've never learned it, could you like tell us what the fingers actually mean? Like
Yeah.
what variables they represent?
Yeah, exactly the same. The FBI, they're exactly the same. The only difference is that like the direction is different because now it's it's generating a force rather than a current in this case. So that's why if you use one rule against the other one, it completely changes it. And similar to the slap rule as well, right? Because slap rule is the opposite as well, if that makes sense. Yeah. So
Yeah, and
same
small
thing.
question with that, would that change the direction, like your actual magnitude? Like not magnitude, but like the positives and negatives if you're using your left hand? Because with the right hand, it's pointing, we know that in the right hand it's going to be positive, and if it's pointing away like towards your knuckles, it's going to be negative. Is that the same for the left hand?
Oh, do you mean so like if it's direction flow? So if you mean that way is positive and that way is negative?
Yeah.
So yeah, it should be exactly the same. The only difference is like essentially left hand rule is different. That's basically
Okay.
it. Yeah.
All right. Okay, thank you.
Yeah, that's so good. Yeah, another question. I'm sorry, whoever's sharing this screen, please stop that. Thank you. Yeah, another question.
Okay, so I didn't actually cover the topic of Faraday's laws and Lenz's laws in my school. So could you like please explain me those topics?
Oh, okay. Yeah, we definitely okay. So I think maybe best thing to do in depth is to probably like look at the previous masterclass because I think we're probably running out of time. But really quickly, if you want to cover it, okay. So Faraday's law is basically the idea that a moving like a moving current that creates like a magnetic field. Well, sorry, the other way around. Essentially, you get an induced EMF if there's like a movement of a magnetic field. So, okay, let me just explain that again. So if you have a change in a magnetic field, right? So if you have, say, a low current and then a high current, right? It'll change the magnetic field, right? So it'll go down, then up, down, then up. Similar to the image that we have in this PowerPoint slide in the top right corner, right? When it's coiling, you get a change in the current as well. So that's called alternating current, right? When there's an alternating current, you also have an alternating magnetic field. That's called magnetic flux. So that change in magnetic field. And that change in magnetic field essentially causes a current. That is essentially what Faraday's law is. There is obviously a professional definition that you need to know that's on the glossary, but that's Faraday's law. Lenz's law. Oh yeah, sorry. Lenz's law is basically the fact that when a magnetic field induces a current, that the direction of that current that it induces will form a magnetic field opposite to the magnetic field that induced it. That's super confusing, I know, but does that?
So is it like they're opposites of each other?
Yeah, for Lenz's law, yes, yeah. So they're opposite because of the conservation of energy, right? So if it forms, if so there's a magnetic field, right, that induces a current. And remember, always a current going through a conductor creates its own magnetic field, right? So if it joins with the magnetic field, what happens? It adds, right? The two vectors add, creates a bigger magnetic field. That magnetic fields now will create a bigger current, and that current will create a bigger magnetic field. And what happens? You have infinite energy, which violates the law of conservation. So Lenz's law states that when the magnetic field induces a current, that current will form, like will go in a direction that is opposite to the direction of the magnetic field that originated. So it cancels out. So it slowly dies away. And that's called loss of energy, which obviously always happens.
Okay, thank you so much. And if I want to like watch your previous master classes, because I have missed those, how can I get those recordings?
I think those should be, so if you go into the Masterclass updates channel in the Discord, and if you just go all like quite a bit up, I think like there should be the recording that's like somebody's probably posted it there. Or you can like, I think in the Discord, you can press a search bar and just search for my name, and in that specific like Masterclass updates channel, and then that should be able to like look at all my messages that have come into the Masterclass updates app, into the Masterclass updates channel, and then you should be able to look through those, and they'll be all there. I will okay, actually maybe to make it easy, I'll just post that recording again if you want. To like after this is done, I'll just post that recording again if that works.
Thank you so much. Could you please
That's okay.
also kindly like share the worksheets that you're like discussing, the questions that you discussed?
Yeah, sure. Actually, the one that I covered before is actually, and I'm in advance, I'm sorry for anybody who wanted to cover the 2023 external exam paper, but that was a question from the 2023 external exam. And the other one was from a textbook. So yeah, I can definitely, yeah, I'll post the slides after, so everybody will have access to that and the recording as well.
Thanks a
Cool.
lot.
Yeah, that's all good. So yeah, about Faraday's law, that's the one that's relevant to transformers as well. So transformer, it's unlikely, and the reason why I say it's unlikely is because it came in the exam last year and it came in my exam, so 2021 and the one last year. So it's very unlikely that you guys will also get a transformers question. However, please learn it. Okay, it's still a high yield. It in general, it's high yield. Maybe for you guys, not as a high yield, but for you guys, still 100% learn it. It's a very important concept, okay, to know, and why we use transformers as well. But yeah, we're like really pushing on time here, so I'll unfortunately have to skip this transformers explanation. All right, Unit 4 special relativity. Who doesn't love Einstein, right? All right, special relativity developed by Einstein 1905, straightforward, essentially deals with anything that travels at the speed or close to the speed of light. We do still, I wouldn't say feel relativistic effects, but it's negligible. It's basically zero, like what we feel, right? Because we're traveling at like 100 k's an hour is nothing, right? So it at speeds closer to the speed of light is when it actually becomes noticeable changes, right? So yeah, that's where essentially the limits of Newtonian physics, or what we call classical physics, essentially comes in. And muons in the atmosphere, very high yield thing to know. It's like basically in every textbook, so you can just look over it. But essentially, it's where a muon comes. It's not supposed to, according to the lab defined lifespan of a muon, it shouldn't be able to come from space all the way down to the ground, but somehow we detect it on the Earth surface, which is a normal classical physics. If you just use speed equals distance over time formulas, it should not be seen on Earth, right? So that's where essentially classical physics, kind of fails a little bit. So, but if you take into account time dilation and length contraction, then it's the muons are explained, right? Remember to know two postulates of special relativity. So the speed of light one and the physics laws of physics one. Is that the same? Okay, I think I just added something at the end here. Since light speed is called, oh yeah, okay. to remember how like what happens when like the light speed and everything, just keep in mind, okay, if you're on a train and the train is going at the speed of light, right, and the train is passing a train station, so this train station is considered stationary, you are looking on this like the train station, and you can, apparently it's a see-through train. Obviously it's unrealistic, it's traveling at the speed of light already. So if it's a see-through train and you look inside the train and you can see someone flashing a torch from one end of the train to the other end. Let me just draw this out. All right, so if this is the train, right, you have the train station here, right, and then you're here, you're looking at the train, so this is the train, keep in mind, and then there's a person on one side who's shining a light from one end of the train to the other end, so it's coming there and coming back here, right? So to them it just goes forward and it just comes back, the light, right? But for the stationary observer on the train station, what will they see? They'll see the light traveling like this and traveling back, essentially, right? And just keep that in mind. I think there's a video on YouTube about it. I want to say it's Crash Course, I think that's the YouTube channel, right? But the physics version of it. So yeah, I think just keep that in mind of how time dilation works and who experiences the time dilation. It's very straightforward. If you just keep this like experiment in mind, that's really good. Yeah. All right. All right, simultaneity, very briefly. Two events that are simultaneous in one frame that may not be simultaneous in another. Again, it's a good video. There's a good video on YouTube that like visualizes it for you guys. But essentially, it's where if it's speeding at the if there's a train, again the same train, if it's at the speed of light, obviously it will go to the lightning closer. So if there's two lightning strikes that strikes the front of the train and the back of the train, right? The front of the train will be moving towards the lightning strike, but the back of the train will be moving away from the lightning strike. So the back of the train should come after, the strike should come after than the one at the front of the train. So it's not simultaneous then. Whereas, but if you looked at from a stationary observer on the train station, you should see it hitting at the same time. So that's essentially the simultaneity kind of thing. But yeah, the light reaches front. This is also the same thing as our flash on a moving train. There's always different like variations essentially. Cool. Why is this not going to the next slide? All right. Oh yeah, paradox of relativity. This is very high yield. You get when you go through a lot of questions, you'll notice that it comes quite a lot. But essentially, twins paradox. One twin goes on a spaceship, goes to a different planet, and obviously it's traveling at speed of light. The twin on Earth stays on Earth, but they come back younger, right? So that's very important. Make sure you know the solution to that as well. And the lad in the barn also knows the solution, but it's essentially like length contracting. And that's why it can fit inside the barn, but that's very high yield. Cool. Oh, sorry, yeah, was there a question?
Yeah, quick question. Would these be like multiple choice where you just identify what the thing would be? Or would there be any short answers for this?
For the paradoxes?
Yeah.
Yeah, for
Or
paradoxes.
like just any definitions.
Oh yeah, for paradoxes, definitely most likely they'll give a short answer for that one because they want you to explain the solution to it as well and like the paradox. In terms of multiple choice, for multiple choice, for simultaneity, they'll probably just ask maybe just like a multiple choice. They could just ask that, like, what is simultaneity, and just give a multiple choice. But again, simultaneity could also be a short answer as well, like explaining how simultaneity works, because I've seen a short answer on that as well.
Right. For the paradoxes, would there be any keywords they'd be looking for? Like that you need to include? Good
question. Time dilation, length contraction. Those are the two biggest. Sorry, that's a very like I guess obvious kind of answer. Those are the main ones. I know like a lot of people who don't mention and just say relativistic effects. That's not enough, right? You have to mention how time dilation, like because remember when you consider relativity, time dilation, length contraction do not occur independently. They are together. One cannot happen without the other, right? They compensate for each other. So when you talk about time dilation, talk about the length contraction as well. That's probably the biggest like keywords. Like they will definitely be looking out for those words. Everything else comes really down to your explanation. But yeah, really good questions. All right, quantum theory. All right, okay. The reason why I know quantum theory might seem like really like not great, but the best way to learn quantum theory is as a timeline. Okay, so how actually something I just realized I forgot quickly about the special relativity. Make sure you know E equals mc squared, so the mass energy relationship as well. Just keep that in mind as well. But yeah, all right. Going back to quantum theory. All right, yeah. Remember this as a timeline. Okay, so essentially, as you can see, before 1700s, right, when essentially Isaac Newton dominated, right, he was like, okay, light is a particle, right? Everyone's like, yeah, I'll take your word for it. We're all good. Let's keep it as that, right? And it quite well explained reflection, right, and refraction as well. Like it somewhat explained what it was, right? However, then, as you guys definitely should know, 1801, Thomas Young, that's when he performed the double slit experiment. And this one is very high yield. This stuff is very high yield. You need to know the exact kind of mechanisms of how it works. Essentially, small two slits that are very small, same wavelength as the light. So it could be like, 540 nanometers, right? It shines through the two slits, and essentially the interference pattern that they see on the other side of the two slits, right? They'll see interference bands, right? And the bands do not match up with if it was a particle, right? So if I were to really quickly draw this out, okay, so we have this is well, if you imagine this is the sheet behind it. So again, flash, right? So I'm just gonna get my water bottle here. So this is the flash, right? It goes through a board with two slits, so the light can just come through the two slits. And then where does the light go? Through a backboard, and this is the backboard, right? And you see dark bands. These are the dark bands. So all of this is light that you see here, and then these are all dark bands, right? They should, if it was a particle, you should only see two sections of light, right? Everything else should be black. It should be dark, right? Because the light would just fill into that slit where the slits are, and that should just be where the light is. But how do you get multiple light areas is because of a proper wave characteristic, right? So essentially where the light goes through the slits, and then it essentially has constructive and destructive interference. And that's essentially where, like, if you best thing to is watch a video on it, because it's best to visualize it. But you can see where the waves essentially come in together. That's where it cancels, and where they don't come in, it's where essentially like they construct. So the constructive bands are essentially where you see the light, and destructive bands are where you see the dark bands. So there's no light there, and essentially that's just what it just proved a point that it was a wave. So everyone's like, okay, this is definite proof that this is a wave, right? So it's a wave. Great. End of story, right? But no, it isn't. Photoelectric effect, right? Again, another high yield one, 1887, the photoelectric effect. So Heinrich Hertz, I think from memory, it was not Hertz himself. I think it was a student or something like that. But Hertz, he discovered electrons, specifically photoelectrons, right? Are ejected from a metal when light hits like a metal, right? So when you have apparently this is a metal, light hits, you get electrons, photoelectrons are shooting out, right? That's something he couldn't see. So according to threshold frequency, according to wave equation, all of that stuff that he essentially changing the intensity of the light, changing the frequency of the light, changing the wavelength of light, all of that, essentially from that he proved that it was a particle then as well.
So,
Yeah.
shouldn't black body be in between Einstein's photon theory, like just before it?
Yeah, exactly correct. Yeah, you do have the ultraviolet catastrophe, right? So that's essentially where you have I forgot exactly when it was. I think it might have been 1800 somewhere, right? But essentially it's where you have this is a really good point that you brought up. Essentially you have a black body, and then when it was heated, they couldn't explain the spectra of light that you saw. There's multiple essentially wavelengths of light that were released, and that's essentially where the classical physics wasn't able to explain that essentially, right? And I think there was a specific law that they used like in classical physics, but they couldn't like calculate the energy, and that's technically in between, which is a really good point. You guys probably should know that. I think ultraviolet catastrophe is covered in the textbooks as well. So that is important. Yeah. So yeah, definitely look on that. That's a good point. Yeah, and then Einstein photon theory comes after. So essentially where he's like, it comes in packet of energy. So it's called photons. That's the reason why he won the Nobel Prize in 1921, not the general theory of relativity, because nobody believed him. But anyway, that's a different point. And then finally, you have the wave-particle duality. This part I highlighted because you need to know the wave-particle duality, but you don't need to know about the de Broglie, like this is you'll probably see de Broglie quite a bit interstate papers. But essentially he proposed that like electrons also behave like a wave and particles as well. And now essentially with Max Planck, with Planck, Einstein, all of that they did, like essentially the modern view now is that they both act as a wave and a particle, if you can get your head around that. So yeah. Cool. But yeah, whoever pointed that out, that's a really important thing. I do want to like again highlight that again, very important, black body radiation. So that was within this timeline here and should have been. But I think I just took it out because it wasn't I guess too many words maybe. But it is a high yield thing. So if you guys want to search it up, ultraviolet catastrophe, black body radiation, right? So that's essentially what classical physics couldn't explain the heat emitted or the number of wavelength that was emitted from a black body, right? Which is a black hole or whatever, anything really. Okay, yeah. So, okay, no, I did bring it in, but I think I put it after. Okay, so we know what a black body is, right? Something that absorbs and emits all radiation. Obviously, it's not real. There isn't a perfect black body. There is some, partial black bodies, like where they do emit and then they absorb all the energy and then emit some of it out, right? That's just like metals, like all those things. But there's no perfect black body, right? And yeah, and then as I mentioned, they fail to explain the spectrum, right? So so if you heat up a black body, right, you're absorbing energy. As the temperature increases, it emits the radiation, right, over like so many wavelengths, like all these colors, right, forming that continuous spectrum. And this can be explained by Wien's displacement curve, right? Wien's displacement curve is the one that releases all the ultraviolets. And what was the problem with classical physics, right? They tried to calculate how much energy is emitted at each wavelength, right? So, and according to the classical physics, at longer wavelengths, right, it worked out. The emission matched well, right, with the absorption. But at the shorter wavelengths, right, energy just infinitely it increased infinitely, and that was the issue because obviously that you can't the hot object can't emit infinite energy in the UV, right? That obviously doesn't happen, and that came known as the UV catastrophe or ultraviolet catastrophe, and that's when Max Planck came along, right? Legend. Essentially, he said it isn't continuously emitted. Energy isn't continuously emitted, right? That's when he proposed quanta, right? That's like proposed energy, so small packets, right? Energy comes in small packets called quanta, and that's when he brought in E equals hf, so energy, right, equals h frequency, so h is a constant, right? Planck's constant specifically, and then that's when he but he brought that in, right? And that's the foundation basically of quantum theory now, because essentially the foundation is that energy comes in that those discrete packets. Discrete meaning that they're not continuous. Okay. All right. That was a very generalization of quantum theory. Okay, photoelectric effect, we kind of covered this. I think I was planning on putting it again because I wanted to talk a bit more about it in terms of the thresholds and stuff. But essentially is if light was a wave, right? If you had light shining on a metal, let me draw that out. Okay. If you had a piece of metal and you have a torch, right? And you have light shining on, right? If it was a wave, like the atoms in the metal, what would the atoms in the metal do? They would absorb the light energy as a wave. They would absorb it continuously. And then over time, it would have enough energy and then it would emit out. But that didn't happen. That's not what it showed. That's not what this experiment showed. What happened was you can shine as much light as you want onto that, but it didn't emit out. Only if you reach that required frequency, or in other words, the energy. So threshold frequency. As soon as you like go above the threshold frequency, that's when the electrons were emitted. And why? Because if light is a particle, then what happens? The particle hits the metal atoms, immediately transfers all of its energy to the metal atom, which ejects it immediately, right? So if you have less energy in that photon, then it'll give the metal atom less energy and it won't emit. That's why you need a threshold frequency. That's why you need a threshold energy level. That's for how much to emit, right? And that's proved that it was a wave, that is a particle over a wave, right? All right, let's keep on moving. Yep, work function, we cover that. All right, this is also a common like a short answer question. Wouldn't be too many marks though, but Rutherford model versus the Bohr model. Hopefully we know who Rutherford and Bohr are. They're very famous scientists who essentially figured out the atom, right? Well, not the atom, but they figured out models of the atoms, right? So the very important to the gold foil experiment, right? So it's essentially where he just scattered alpha particles, right, through the gold foil, and then he just saw the scattering of that basically. But essentially, point is that most of those particles that he shot were passed through. So then what he identified were through the gold atoms, that mostly was in empty space, right? Because if it was more matter over empty space, then it would hit the actual matter, it would hit the atoms and it wouldn't scatter. But if it's empty space, it'll just go right through, right? So anyway, atoms are mostly empty space, and that's referring to the electron cloud around it. But some deflected sharply, which just means that there is some sort of nucleus there, and it's probably positive just because of alpha particles, right? And then essentially the important thing you need to know is the summary and the limitations here. So Adam, what he figured out was the central nucleus containing protons, later neutrons, electrons orbit nucleus like planets around the sun. So he thought it was like electrons just orbiting it right in the sun, and that keep that in mind because that's a limitation later on. So what's the problem? The limitation was couldn't explain why orbiting electrons don't lose energy and spiral into the nucleus. Okay, so this is the explanation here, and this is good. We call it circular motion. Is the first limitation is based on this, right? So essentially, if you had it moving around in a circle, because of centripetal acceleration, it should come in and collapse into the neutron. Not neutron, nucleus, right? But that obviously doesn't happen, right? It means that like if it comes in and it like goes into the nucleus, that means the atoms are unstable basically and collapse. But obviously they're not. The atoms are pretty stable. So that there is that's one limitation. And the other one is fail to explain discrete spectral lines in hydrogen's emission spectrum. So this is basically identifying that when like specifically for a hydrogen atom that the line spectra which weren't explained. So what they emitted from that, right? Bohr model fixed that. Some of it, just remember Bohr's postulates. I think it's like electrons like in an atom exist in like stationary states or whatever, and another one, just make sure you know them. And then just keep in mind equals HF, so the absorption emission spectra. So when something is absorbed, it will emit in the same level. Something like successes, why I put successes because it fixed the Rutherford's model, is that it explained that line spectra. So each line equals a photon emitted. So because of the movement of electrons down the shells and up the shells, they could explain that, right? But it only worked for hydrogen, and they couldn't explain more complex atoms or fine details of the spectra, right? I know that's pretty general, but there are a few things like there's like the Zeeman effect and stuff like that. That are probably important. And this kind of refers to like the things that I think we learned it in grade 11 physics about like the Lyman series, Balmer series, and the Paschen series, right? So n equals 1, n equals 2, n equals 3. So it goes up. Those are the emissions that relevant to the Bohr model. Standard model, super easy, right? Just memory. Now, again, this is basically the only part in the whole syllabus that you should be memorizing, all right? Apart from definitions, potentially apart from like exact law definitions like Faraday's law, Lenz's law. But even then you should be able to explain Faraday's law and Lenz's law without, memorizing it still, right? But apart from that, this is the only part you need to memorize, right? So like what are like all of the particles, right? What are like the 4 fundamental forces in which particles maintain that? and you can use flashcards. I do have an Anki deck that has a lot of the flashcards, which I can potentially put into Discord if it can fit. But yeah, there's like maybe 30 cards in there. They're basically all of the stuff that you need to memorize for the exam, right? All right, any questions before I go into like pieces of advice? Hopefully not. I haven't been monitoring the chat, as you guys know, so probably just speak out if you do. All right. Final thing, we're about to finish up. Hopefully we can finish it by 9:30. Understand, don't memorize. I've been kind of preaching about that whole time. I can guarantee that like it's very, very difficult to get complex unfamiliars, which means it's very difficult to get any hundreds or close to hundreds if you just memorize formulas and applications, right? So please do not just remember the formulas and how to apply them. Just be like, okay, I insert this function there, insert this there. Because I see a question, but I'll really quickly explain this. But for the previous question where you had the circular motion connected to the inclined plane, people would not know where to put the mass, would not put different things, because it's an important thing to understand what forces attached to what, right? Going through the golden rule. Okay, so yeah, question there, the first person who put their hand up.
Are you also gonna be like going through the practice questions in the next few master classes?
To be fair, I didn't think of doing another masterclass, but if it is something of interest, maybe I might have time to do one. Yeah, I'll try and figure out if I can do it. It's just, yeah, my exams are getting pretty close as well, so it's not ideal timing. But yeah, I'll see if you guys definitely. I'll try, and if there's enough interest, I'll definitely try and go through some practice questions too.
What type of
another master.
structure do you follow for answering your questions? Like any exam question?
Like a calculation question or like an explanation question? Or both?
Explanation. Like what type of structure do you follow?
Yeah, explanation question. So yeah, it really depends on the type of question. But I think like starting off with the actual question itself, right? So what is it? If it's like, okay, let's just say if it's explain transformers, right? And associate Faraday's law or something like that, because that was one of the questions in my exam, right? Essentially, start off with what Faraday's law is. Okay, explain the exact. Like I memorized the Faraday's law definition, but obviously you don't need to if you know the gist of it. Remember, understand, don't memorize. But I would start with Faraday's law, then I would explain transformers and bring that definition into it. So then I would essentially explaining how transformers work. Okay, so what is it made up of? Transformers is essentially an iron core with two sets of coils on both sides, ensuring that only alternating current works for it. And then Faraday's law is because the changing in magnetic flux there induces a current in the other side of the coils, which essentially brings the current, and that's how you can So that's kind of how I'd bring this. So explain Faraday's law, explain transformers, bring Faraday's law at the end and apply it. That's kind of like a specific kind of one, but yeah, hopefully that kind of gets it.
And for the calculation-based questions, you isolate all the different parts, right?
Yeah, but yeah, I isolate different parts, but make really important to bring it back together. So make sure everything links together at the end as well. Yeah.
All right. Thank you so much for this session.
That's so good. Next question there. I think there was someone else who has their hand up on second. I'll lower that person's hand.
I'll just go because the first person isn't going.
Yeah, it's got a lower hand.
Yeah. About the Transformers question you just talked about, you said something about like the context about like iron core and stuff. Is context important in physics, like for marking guide's sake?
Oh yeah, no, probably not for marking guide's sake. No, definitely not. Like like understanding that it's an iron core and like why transformers are used. I mean, you need to know that it's like a step down, step up, so it's voltage changing. But why we use it in the real world, that stuff is not really important. But I can guarantee you, knowing that stuff will ensure you understand it like 100 times more. So you should be able to get any question. You should be able to know that question because you understand that context. But no, you're right. In an exam, in marking guide's sake, no, it is probably not important now. Good question though.
Yeah. Also, along with that, on the slide, I see you have history and timeline. Is it the same thing as context for that?
Yeah, exactly correct. So one of the ways that I like to understand things is first of all through like I guess I know this is kind of stupid, but etymology, which is like, you know, the where the word comes from origin wise. It's pretty hard with physics stuff sometimes, but that's one way to understand. But also real life context and history and timeline. Those are ways of understanding concepts, because I didn't want to just like, you know, blindly preach or understand, don't memorize. I wanted to actually give like methods of actually doing that. So yeah, history and timeline is important. That's how I understood all of the wave particle duality stuff, right? Like actual progression of what it is. And yeah, that is a way of, that's context, and that's a way of understanding that concept overall. But yeah, good question. I think the other person probably put their hand down. All right. Yeah. So yeah, I think yeah, formulas are so overrated. Definitely are super overrated. So please, yeah, again, no formulas are like blind application of it. I mean, obviously, worst case scenario, if you don't know like what the question is saying, then just chuck formulas and you might hopefully you'll get marks for that. That's the way of definitely, you know, getting marks. Do not ever leave a question blank. But yeah, again, formulas are overrated. After you understand the concepts, right? So after you know, you're like pretty sure, like, okay, you can probably, I can probably answer a lot of the questions, right? Practice papers nonstop, right? Now, I don't want to stress anybody out, but I'm like it is ideal if you guys are at that stage now. You're just practicing papers nonstop, right? Because it's about a month away. This would be an ideal time. However, again, I don't want to stress anybody out. Like if you're not at that stage, it's okay. Maybe next week start doing like past papers. Because the thing to keep in mind is you guys are doing like 5, 6 subjects. Some like ideally, most of you guys might be doing 4, right? That's the minimum number of subjects I would imagine most of you guys are doing. So there's a lot of subjects you guys have to manage. So it's not like you can do physics every single day until it, right? So yeah, keep that in mind. That yeah, to just do practice papers nonstop after you understand content. If you have time, do like state exam, the interstate exam. So like WACE, HSC, VC. Those are the main ones. Yeah, just do those. Like they are very, very good in understanding if you actually know what you're doing, right? Because QCAA, like, you know, they might have like some wishy-washy like applications, right? But the VC, HSC ones, they like you really need to know what you're doing for those things. Yeah, question. Trying.
Yeah. Not you said. I mean, would you have any practice like worksheets that are specific to topics by any chance, or you know where to get them from?
I might have some, but yeah, if you're looking for like paid resources, there definitely is. I think like there is a Cambridge version and Oxford version of each one. So I think it's called like Oxford Study Buddy, I want to say, and there's a Cambridge version as well, I think, or Cambridge Checkpoints, I think. And then there's a Pearson version as well, and they will have so essentially you have the normal textbook, right? The Oxford textbook, Pearson and Cambridge, but then they have like their worksheet practice question version of like smaller ones. If you're willing to spend the money, those ones will have like topic tests, like each topic will have a test, and most likely they'll have mock exams at the end as well. So worth investing if that's what you're looking for. But keep in mind, always look at like what the contents pages are of all of them.
All right, thank you.
That's so good. Yeah, cool. Now some general advice just about external exams in general. Yeah, so super important timetabling. I just mentioned that. Actually, I'll quickly just show you guys my timetable that I had when I was in year 12. I can send if anybody wants again, I can send like a empty version of this. All right, let me share the screen. But this was, I think, yeah, like not too long. So if you think about it, so this is 2021, right? Wait, this is not sharing, is it? All right, cool, it's sharing. Okay. So you can see this. So it's all gray because every day after the day is finished, I grade it up, right? So imagine if this is all white essentially, and then the day that it would be, like if this is today, this would be orange, and then any day before that would be gray. Essentially, I had 6 subjects because they didn't have the option to accelerate. So I kind of like associated a subject every day, right, until the date. So like here we go. This is from the 5th October. So this would have been like me last week. 4 years ago. Jesus. Okay. And then till the date, basically. So you can see like the actual externals are Oh wait, no, that's not the actual standards, but point remains, right? And then I would have a tracking, like I would have a counter. So this would be how many sessions that I would have associated with it. So I would want more specialists because that was the harder one for me. I would want more chemistry because that was also harder. But physics wasn't too hard. Biology, I think, just didn't have that many resources. And then methods wasn't too hard either. So like I've like associated based on like which ones I found like personally my strengths, personally my weaknesses. And then obviously English, I have to put a ton because you know who likes English. Um so yeah, and then that was just my timetable. It was basically an hour to hour, so from 5 a.m. an hour to 10 p.m. Now usually I would never tell anybody to do an hour to hour timetable, but because it's a month out, I would, right? I would definitely recommend to do an hour to hour. Otherwise, like days will just go by quickly. I do have an empty version as well. Yeah, cool. So that's what I used for scheduling. I'll share this. All right. Okay. Other one's Anki. Hopefully you guys have heard it, but I'll briefly mention Anki quickly. But Anki is a flashcard app. It is literally the GOAT of all flashcard apps. Trumps every other single one, Quizlet, whatever else. Like nobody really cares about that. Anki is the one. It's used like literally. It is like the basis of all med students. Like I use it every single day basically. But keep in mind that this is mainly for memorization. Anki flashcards are used for memorization. It's a memorization tool. So if you guys do, for example, do bio or even certain aspects of chemistry, and obviously standard models types, Anki is like super, super good. It's open source and it's free on like laptops. Sorry, not laptop, PC, right? Windows. On the phone app, it does cost money though. All right. Study app, I was just saying to just not procrastinate, that's all. In terms of AI, okay, now like obviously you guys don't have any assignments left, so like please use AI to the max. Okay, AI is kind of super good. ChatGPT is obviously really good. Perplexity AI. So if you want to create any practice questions for yourself, I've found Perplexity AI is quite good in creating table questions. Because ChatGPT doesn't really create good questions that involve data tables, so that's a good one. Notebook LM, so that's the Google version, so created by Google, so like Gemini kind of things. Notebook LM is really good. So if you do a lot of driving, or if you go on like in the next month you're driving a lot for some reason, or if you're in the car a lot and you're like don't want to, read anything because it feels like bad or something, and you want to study, Notebook LM is really good because you can upload any resource. So you can literally upload a whole textbook and then convert it to a podcast, and the podcast you can just listen to whenever you're like, whenever you want while you're driving. Don't quote me about this, but apparently listening to while you sleep apparently is good as well. But don't quote me. I don't know the research behind that. Cool. Otherwise, yeah, that's about it. Finished 9:30. If technically it's a Q&A time now, so if you guys do have any questions, but otherwise feel free to leave. Thanks, guys. I'll just chill out here for a bit. Thanks, guys, for staying. Have a good night. Good luck for your exams as well.
Thank you so much for this session as well. Have a great night.
That's so good. Thank you for your questions. Bye.
Thank you. Bye.
I just had
Oh,
a
I have a
quick
question.
question.
Oh, no, you go. You go.
Oh, do you? No, you can go first. It's okay.
Thanks. So with the explanation questions, so you know
Yeah.
how you had something like the ideal question guide for the data test, data graph stuff?
Mm.
Is there something like that for explanation questions, like explain electromagnetic radiation or explain photoelectric effect?
Oh yeah, good question. I didn't personally make. Only reason why I didn't is because like when I went through like so many practice papers, I just noticed a trend. Like I just noticed a pattern within the data questions. Like literally, like the marking guide says the exact same thing basically every single time. I think the reason why I didn't make one for the explanation ones is because it varied quite a bit. However, that is a really good thing that you bring up there, because, for example, for the explaining the paradoxes, explaining, as you mentioned, Faraday's law, Lenz's law, you will see that quite a bit in your practice. You'll see like a very similar question. So definitely, I would create one if like if you see that quite a bit. But just because the questions change quite a bit, like I didn't create one personally, but the structure probably stays the same. I can probably take a look at it if I have a bit of time, just to see if there's any like patterns in how they like structure it. And I'll let you the chat know. But yeah, good question there.
Yeah, thank you.
That's so good. Have a good night.
I had a question about the data booklet. In the quantum theory part, they have Rydberg's constant and Wien's displacement constant. In
Yeah.
my school, we've never really done any practice on those, like even for mocks. So would you be able to quickly tell me what that is?
Yeah. So what was the first one? The first constant, sorry, that you mentioned.
You want me to put a screenshot in the chat? If that
Oh
helps?
yeah. Yeah, that might help. Yeah, if the chat. Yeah. Okay. Awesome. So awesome. Yeah, the chat's working.
Okay.
Yeah. So I'm just reading the chat out.
Oh,
While he's doing that, do you mind if I could just ask a question?
Yeah. Sure.
About the standard model,
Yeah.
have you seen a lot of questions that involve like, you know how each particle have like their own, there's like a number to it, like 2/3, 1/3 or something like that?
Oh, yep. The baryon and lepton
Yeah,
numbers.
not lepton numbers. Yeah. Have you seen a lot of questions that I think from the top of my head, like you have to do addition or something with regards to that? But I've seen some in my textbook, but I haven't seen much on externals. But
Yeah.
not sure if it's a high yield, maybe.
Yeah. You're right. It's not high yield. It's very low yield actually. You see it a lot in like the interstate papers because I think they do cover that quite a bit. But yeah, you don't see them at all basically like in the QCAA. You
Yeah.
do have to know those formulas because but they're simple addition as you mentioned, right? So like you don't need to know like them that much, but I would definitely like make sure to remember those formulas. But again, the problem is that those formulas are not even on the QCAA formula sheet. So, I doubt even that they would ask it. I'm very wary of saying like don't study for those things because obviously you should because it is kind of hard to just say don't study and study. But definitely it is low yield. I can guarantee you that it is very low yield. I have not seen that yet at all as well. So yeah. So the chat, yeah, Rydberg's okay. And was the Wien's one, right? So yeah, so Wien's constant is used in like the Wien's displacement curves and black body radiation, right? So let me just look at the formula, the displacement. Yeah, so I don't remember exactly the formula. I forgot exactly, but it's something like B over something, right? But essentially, it's used like black body radiation when something is absorbed and it emits all the wavelengths of the color spectrum essentially. But there is one wavelength that is always the most intense. And that most intense one is what we see, is what our eyes see. So to us, it might look like only one wavelength being emitted, but all wavelengths being emitted, but only part. Yeah, exactly. There you go. Yeah. So essentially that's a good one. The what is that? Lambda, right? Lambda max is the peak wavelength. The peak wavelength means the one that I just mentioned, where it's the most intense wavelength that's being released. So again, I'm just going to repeat. All the wavelengths are being released, right? But there's one wavelength that is the most intense, and that's the peak wavelength. That's the one we see. And essentially what they did was every temperature has a different peak wavelength. And that they've essentially Wien basically created a curve that essentially plots that peak wavelength to the temperature. So I forgot exactly, the formula shows it, but if you increase the temperature of the like peak wavelength decreases, right? that kind of makes sense actually, right? So yeah, and that's kind of essentially Wien's displacement curve. So just keep in mind, like it releases all of the wavelengths, but only one is what we can see is the peak wavelength because it's the most intense. Remember what intensity is in terms of light as well. It's just the number of photons that are released. Cool. Does that make sense? Hopefully, yeah. And that's and obviously the Wien like this constant is just used in that. Yeah, cool. And then the Rydberg's, I think Rydberg's is really low yield, but it's like for spectroscopy. It's like basically like I think it's like hydrogen, something for hydrogen. But it's like used for like that electromagnetic spectra of like the hydrogen atom or something. But very low yield. I don't think you should learn that. There's no point of learning
Is that like
basically.
the thing where you jump from one electron level to another?
Yeah, basically the emission and absorption spectra. Yeah, exactly. Yeah, but I'm like, if like worst case scenario, if it does pop up on the exam, you'll definitely know which one to use. Like you can kind of like work out from the variables that they've given you, kind of stuff. So yeah, cool. There's
Alright,
been
thank
a
you.
few questions. Yeah, all good. Thanks for the question. Is the ground state 1 or 0? Sorry, just really quickly in the chat. Is the ground state 1 or 0? Honestly, I wouldn't be able to tell you. I'll be honest with that. I think Rydberg has been so low yield that I haven't like removed it from my mind. Sorry about that. But yeah, the person with the hand up.
I forgot my
Um,
question. Oh. Hello?
Oh yeah, hello. Yeah.
Yeah, hey Suka, so for the Anki flashcards, you said you were able to give them out for like physics, right?
Yes, yeah.
Okay,
Potentially.
so
I'll have to see if the file size is not too big. But yeah.
okay, well, is this like a link or like how would I be able to access the flashcards?
Yeah, a good point. Okay, so there's the actual flashcards themselves, like the file is .apkg, so it's like a different file extension. But essentially, you need to download the Anki app on your like laptop.
Yeah.
And then once you click the app, you'll download it, and then when you open it, it'll just automatically open up in Anki, and you can import, and then it'll just show that deck on there. And point is, you just cover all of that until you memorize it properly, and then you can just cover it the next day, and just cover it every single day until the exam, basically.
Okay, cool. Do you also have one for
Yeah.
chemistry?
Yeah, I have one. Yeah, for chemistry, bio, and physics. I'm pretty sure. Yeah, so I can try and send those across. I'll try, and maybe I
Please.
can do like yeah. I can try like do like an Anki, small Anki like masterclass 30 minutes or something because it is kind of confusing just to get your head around that at the
Yeah,
start.
that would
So
be good. Yeah, okay.
yeah,
Okay.
beautiful.
All right, thank you very much.
All good. Any other
Um,
questions?
hello.
Yeah. Hey.
I just want to ask, for the Anki flashcards, are you gonna put that in the Discord or like is there a way to access them?
Yeah. So if I get it to work, like if the file size isn't too big and stuff, I'll put it in the Discord. Yeah. So either one, I'll just chuck it into Discord straight away, or I'll try and like upload it to a Google Drive or something, and then just chuck the link in there. Either one. Yeah.
All right, sounds good. Thank you. Thanks for the lesson.
All good. No worries.
I'm just asking, are you able to do like a masterclass for chemistry, like Unit 4?
Yeah. Oh, I love organic chem. Yeah, I can. Okay. Yeah. So, I'll have to like organize the times. Is there no one else doing the chemistry one?
I think there was one some time ago, but I kind of forgot to go there. And I think your explanation's like really good, so it'd be pretty helpful to.
Oh, okay.
Yeah.
Okay, yeah, no, definitely. Thanks for that as well. That's good feedback. But yeah, definitely I'll try and like check out like a timetable and see if I can like put in a chemistry and then potentially hopefully another like physics one and maybe even an Anki one potentially. But yeah, I'll see what I can do, definitely. I'll
Thank you.
check all that. But that's like that you brought that up, so I can